The second part of section 3 is going to be about two main topics: the concept of concavity, and then along with that, the idea of points of inflection. Now, this is going to help you to clarify those kinds of cases where you have critical points, but they're neither maximums nor minimums. This is going to help clarify those kinds of situations in a couple of the first derivative tests that we did in the first segment of section 3. So we're going to start with a definition of concavity, since that's probably a new term that you haven't heard before, and this is also going to lead us into a discussion about points of inflection. Okay, so concavity sort of sounds like bad things, right? And that's kind of appropriate since we were talking about braces last week, so that kind of fits well. So concavity is not a problem with your tooth, however, they have a similar root word. But concavity concavity is a characteristic that we describe about a graph. Just like the idea of a graph increasing or decreasing, a third characteristic is the idea of a graph having a particular type of concavity. Whether the graph is essentially facing upwards, if you think about like a parabola facing up, when we describe parabolas, we say they face up or they face down. We're actually describing the concavity of the graph instead. If we say that it faces up, we call it concave up. If we say that it faces down, we call it concave down. And there's a connection between this concavity idea and the idea of the derivative. So that's where we're going to be able to analyze the concavity from. So the official definition for concavity: the graph of a differentiable function, of course your function must be differentiable for us to be able to describe the concavity of it. It is considered to be concave up, notice on an open interval. The definition of concavity includes open intervals only, so that will give you a hint on how you're going to write intervals when you do homework questions. It's concave up on an open interval if the derivative is increasing. The derivative is increasing. So what is that referring to if the derivative is increasing? The slope of the derivative. What's another word for the slope of the derivative? So, acceleration, which is which kind of derivative? The second derivative. So concavity is going to relate to the second derivative because we're talking about the increasing characteristics of the derivative. So we're having to go to the second derivative to determine the concavity of the graph. So that's an important feature because so far we talked about the first derivative test, and that was pretty clear that we had to use the first derivative to do that. Now we're jumping to the second derivative. A graph is considered to be concave down on an open interval if the derivative is decreasing on the interval. So that's just the opposite case. Your graphs are either concave up, concave down, or they have no concavity. No concavity implies that your graph is the derivative is neither increasing nor decreasing. So that would be something like the derivative is constant. If your derivative is constant, then you're going to have no concavity to your graph. What do you think might be a type of graph that doesn't have concavity? A line. Because the derivative of a line is a constant number. And constant numbers aren't going to be increasing or decreasing, they're staying the same. So lines are the one kind of thing we can't really describe concavity for because they don't have a facing up or facing down. They're just straight lines. So the key thing about concavity is we're looking at the second derivative now. So you're going to need to be able to go to the second derivative for a lot of the different types of functions to be able to determine this piece of information. This is also going to build the foundation for us talking about the second derivative test, which is the third segment of section 3 here. So we'll be getting to that one as well. So let's use concavity in a more general sense. And we'll also look at a couple of different examples that are going to ask us questions about the concavity of the graph. Here is the official concavity test. Just like the first derivative test, this is the official concavity test. Concavity test is going to help you to determine if a graph is concave up or concave down. Now, note that a graph can be both concave up and concave down on different intervals. So just because a graph has a section that's concave up doesn't mean the whole graph is concave up. It'll be based upon intervals of the graph. So in the first section here, we have the graph of a twice differentiable function. Notice that it has to be twice differentiable because we're talking about the second derivative, so that kind of makes sense. We would define it as being concave up on any interval of the graph. Remember, it's an open interval where y double prime is greater than 0. That's all we mean by saying it's concave up, because the second derivative is positive, meaning that the first derivative is increasing. The values are getting larger. It is concave down on a given interval where the second derivative is less than 0. So your second derivative is negative, which indicates that the first derivative is decreasing. So here's how you're going to apply this concavity test that we're talking about here. You're going to need to find the second derivative. So that's different than the first derivative test, because we actually need the second derivative now. You're going to set it equal to 0. That's the same as the first derivative test. We're always talking about setting it equal to 0. You're going to make a second derivative sign chart. We already know how to make sign charts because we did that in the first derivative test, but note that it is a second derivative sign chart instead of the first, which is why the labels are so important, because some questions might be asking you about maximums and minimums, in which case you'll defer to the first derivative and make a first derivative sign chart. Some questions might be asking you about the concavity of a graph, in which case you're going to need to make a second derivative sign chart. So you might actually need both to answer certain questions. And then you'll need to determine which intervals the second derivative is either positive or negative. Basically complete the sign chart the same way you complete a first derivative sign chart. But remember that it's referring to the second derivative. So that means when you plug numbers back in, you're plugging it back into the second derivative, not to any of the previous functions. So it can get a little bit confusing, especially if you're not necessarily very clear about how you work through the problem, to know which function to plug the numbers back into. So the process of the concavity test is basically the same process and steps that you do on the first derivative test, but we're applying it to the second derivative. This is important because you will need second derivatives, of course, when we get to the second derivative test. So it's almost a preview of what we're going to do in the third section. Concavity is sometimes hard to understand because it's not as easy to picture as a graph increasing or a graph decreasing. When you look at a function, it's not always as easy to say, oh, that graph is concave up or that graph is concave down. As we start to build up these different concepts, we're going to be able to start drawing sketches of graphs, and that's where it's going to start to fit together when you picture a graph as well as all of these characteristics about the graph. So we have a lot of different phrases that are floating around right now because we've talked about increasing, decreasing, relative max, relative min, absolute max, absolute min, extremas, critical points. There's all these different terms that are referring to characteristics regarding those graphs. So we want to kind of put all those terms together, and our goal is to be able to put those pieces of information together into a puzzle and then be able to graph what function they're describing. So moving on to the next view. There we go. This is going to seem really random for a second, but I'll explain. It's going to seem completely illogical until it kind of fits together. This is something that I was taught in high school calculus by my teacher. And I don't think Kool-Aid was any more popular then than it is now necessarily. So imagine just any sort of drink. It doesn't have to be Kool-Aid, it's just the example. But if you want to imagine water, that will work the same way. It really doesn't matter what sort of drink we're talking about. Imagine that you have a graph, and your graph is going to be a cup or a bowl. It's going to have to hold something. If your graph will hold that liquid, like Kool-Aid, water, soup, whatever you want it to be, if it is going to be in your bowl and it will stay in your bowl, in your graph, you have a concave up graph. A concave up graph is something that could hold liquid. A concave down graph is not going to hold your liquid. So if it's not going to hold the Kool-Aid or water or whatever your analogy is, then your graph is concave down. So if you imagine you have a particular type of polynomial, let me draw a polynomial here. Let's say we have some sort of polynomial like this. This graph, or this polynomial that I just drew a random sketch for, has both a concave up section and a concave down section. Now let me label this. This is f of x. So that's important because it's not the derivative, it's not the second derivative, it's the actual function. There is a section of this derivative that would hold Kool-Aid. The section of the derivative, or section of this graph, section of f of x that would hold Kool-Aid is over here on the right side. This whole section in here that looks like a parabola facing upwards, if you poured water into that, or Kool-Aid, it would hold that liquid. It would be able to hold that section. So we have a section that's concave up over here on the right. But what would happen on the left side? If you were to pour Kool-Aid into that, what would happen? It would all fall out. It wouldn't stay there. If it won't stay there, your graph's concave down. So this is something you can imagine when you're just looking at a function. I didn't put any numbers on the graph. I didn't give you an equation for the graph or any other information. But you can look at the graph and say, oh, that graph is not going to hold anything, so I would say that it's going to be concave down. Or the other section of the graph is going to hold something, so it is going to be concave up. So you can kind of use that analogy of some sort of liquid example to give you an idea of whether or not your graph will be able to be considered concave up or concave down. You can have multiple segments of each. Just like you can have multiple maximums and multiple minimums, you can have multiple segments that are concave up and multiple sections that are concave down. So it doesn't necessarily have to be mutually exclusive of each other. So if you need kind of a more general analogy, that may help you to imagine what's going on in the concavity test. It's also a lot simpler. Joe?
Is this the same sort of deal though with like a cubic? It's not going to have like the whole parabola, but it's going to be curving kind of.
Yeah. So even if it doesn't have a complete parabola, like this one, I made kind of extreme so you can see it. Even if it just curves, like maybe it stops up here at the top and it cuts off. Even if all you have is what's here on the left side, you would still consider that to be concave down because if you continued it, it would then be the down parabola. So you may only have a segment of the parabolas, but parabolas are a good thing to imagine if you're trying to talk about concavity. Okay, let's actually apply this stuff somewhere. Use the concavity test.
Because we already did one. Yeah, this is the mean. Oh, no, the first year.
That's what it was. Continuous. Use the concavity test to determine the concavity of the function on the interval. Now note that they did specify an interval for you, so that's telling you right away it's narrowing it down a little bit. This graph could be a different type of concavity on a different interval, but the only one we care about is the interval that they specified for us here. So, concavity test. What's the first thing we need to do for the concavity test? Second derivative. Okay, luckily this one's not too bad. What's the first derivative of y equals x squared? 2x. What is the second derivative? 2. Okay. So no matter what the x value is, the second derivative is always going to be 2. The second derivative is constant. So if we were to make a sign chart, we would label it y double prime. But would we have any numbers to put on it? No, because the second derivative is always 2. It can't be 0 if it's always 2. So we don't have any numbers to put on the second derivative sign chart. It's always going to be positive. No matter what interval they specify, it's always going to be positive. Well, that sort of makes sense if you think about the Kool-Aid example. What does y equals x squared look like?
Like it could hold Kool-Aid.
Like it could hold Kool-Aid, right? It's a U shape, it faces upwards, and you pour something into it and it would hold it. So that seems logical that it is always concave up. So they only wanted us to look at 3 to 10. We don't even have to worry about the interval at all because it doesn't affect the answer. So this is a concave, that's supposed to be an E, concave up on the interval from 3 to 10. Now be careful in this section because they are going to specify the intervals in interval notation like this with the parentheses, since we know the concavity test is applying to open intervals, pay careful attention that it's not a point on the graph, it is a series of x values, a starting and an ending x value. So any questions on part A? That one wasn't too complicated. And let's just make things a little more complicated and throw a trig function in there somewhere. So let's do part B. Y equals 3 plus sine x on the interval from 0 to 2 pi. That's also important if you think about a sine graph, because 0 to 2 pi is going to be one period of the graph, but we know it keeps going over and over again, so it may have some changes elsewhere if we look outside that interval. So, what do we need to do first? First derivative. Okay, what is the first derivative? Cosine. All right, that's not bad. What happened to the 3 though? Goes away. It's constant, so derivative of a constant is always 0. Okay, what is the second derivative? Negative sine x. All right. And what do we want to normally do with that second derivative? Set it equal to 0. Okay. Now notice that we're on the interval from 0 to 2 pi, so you only have to worry about numbers that are in that section for your potential x values. Because there's an infinite number of x values that are going to make this equation true. So our question is, when is sine equal to 0? Any ideas? 0 and 2 pi. Okay, so how could we figure this out? If you don't know off the top of your head, what could you look at? Unit circle would be a good one, and luckily these are going to be easy values to find on the unit circle. The zeros, ones, negative ones, those are good ones. So let me make a unit circle up here just in case. Pretend like it's a circle. And then we've got 0 and pi, and 2 pi, and so forth. And this is a sine we're looking for. So we want to know about sine. Is that the x coordinate or the y coordinate of the plane? That's our y. So we want to pay attention to where the y equals 0. Well, for y to equal 0, it's going to have to be on the x-axis. So like this point, it's at 1, 0. And this point is at negative 1, 0. So those are going to be some potential points for us to look at, because that's where we're going to have the sine equaling 0. Now, what about this negative? Why am I not paying much attention to it?
It's just 0.
Well, couldn't we divide by negative 1? Would that change this at all? Not at all. So we could divide by a negative 1. What effect does the negative have on the graph of sine?
None.
It reflects it. Okay. It reflects it upside down, but if it's already on 0 and you reflect it, it's not going to change anything. So it doesn't affect the zeros. Would it affect other points on the graph? Pretty much everything else except for this one case. So this is a special case because we don't really have to worry about that negative too much. So what are some x values I want to list down here? 0 pi, 2 pi. Okay. Now, they did mention this interval. Does this interval narrow it down at all?
Yeah.
For us?
0 to pi.
Yeah, we can't worry about 0 and 2 pi because it's an open interval. It's not including the endpoints. So we're not going to have to be too concerned about what's happening before 0, and we don't have to be too concerned about what's happening after 2 pi, because those are the endpoints on the interval they gave us. So if we make a sine chart, y double prime, sine chart. If you want to label like the ends of the sine chart as 0 and 2 pi, you're welcome to do that, because you know you don't have to go past those points. But make sure pi's on there. That is important. And the unit circle might actually help us a little bit in trying to answer this question. We need to fill out the sine chart. What's some number between 0 and pi we could plug in pretty easily? Pi over 2 would be a good one. Okay. So we just want to know what negative sine of pi over 2 is. Okay, let's find sine first. So what's the sine of pi over 2 up here at the top? 1, because that's at 0, 1. But this is negative sine, so our number is negative. Okay? Something between pi and 2 pi. 3 pi over 2. Okay, that's at the bottom. That is 0, negative 1. So our sine is equal to negative 1, but then what does that make our second derivative equal to? Positive. All right? So we've got our two intervals. Now we just need to describe where it's concave up and where it's concave down. So let's start with concave up. Between what two numbers is it concave up for? Pi and 2 pi. And we know that second derivatives with concavity deal with open intervals. So between pi and 2 pi. And then concave down. What interval there? 0 to pi. Now this would be, of course, different if we had a different interval. So depending on the interval they specify, especially for trig functions, it's going to make a big difference in their answers. Any questions about the process of the concavity test and what you want to do there?
I was just wondering why we use graph.
In the definition of the concavity test a couple slides ago, it said it's only for the open interval, so you know you'll always use the Okay, let me jump to the homework really quickly. Hopefully, this might be a lot of jumping. There it is. And we just did example 2. So that is 7 through 12. Right here. And that has 2 parts to it, so you'll do question 7 through 12, which will be basically just like one of those 2 parts that I just did.